Hello, Tommy. I think let's just wait for a bit more longer to see any other participants would like to join. Just like I said, Brad, I have received 8 acceptance. So other than that, because I sent, in the first place, I sent the invitation. I can see my invitation has been forwarded many times. So I presume there will be more attendees today. So.
Yep, all good. We'll deal with it however many we get. If there's 8 billion people in the world, if they all want to turn up, good for me.
Yeah. And John,
some of them might be a little bored, but
Yeah, yeah. John is also very generous that he's happy to kind of co-facilitate this event. So at the beginning, I would just quickly introduce, ANSHM, and then why we run this kind of web forums in regular basis, and then I will hand over to John to facilitate. So I guess in the end there will be questions as well. So.
Sure.
I don't know that I've got much to offer, Lee. I think you should just introduce Brad, and
yeah.
I'll try and help out with the question time. That's required.
Yeah, sure. Yeah, thanks, John. Yeah, if you can't handle, I can take over. Yeah.
So I think Brad, one of the things that I try and do in my role in ANSHM is to try and provide feedback to the academic teams, and both sort of the nature of their projects, the kind of work that we're doing, where there's sort of, I see the open opportunities for research. And I think even in these sorts of forums, if you know how you find them useful, what you don't find useful, just let us all know, and try and shape it to better suit organisations like ourselves, and find a nice place to play in amongst the multiple different perspectives.
Okay. I think we just let's kick start. It's already 1:03.
چون وقتی مثلا مقایسه می‌کنیم.
You see that somebody is speaking. Can you please, Mary? Can you please mute yourself? We're about to start. Thank you. Okay. We have 14 participants today, and thanks for everyone for joining today's ANSHM web forum. This is our first web forum, starting from the second half of this year. ANSHM is is our Australian network for structured house monitoring, aiming to promote structured house monitoring research and applications for Australian industry context as well as international construction context. So the purpose of setting this kind of a web forum on a regular basis is to raise awareness and recognition of ANSHM in Australia as well as international. So starting from this year, we are going to host regular web forums. So today is our first web forum, and it's my pleasure to have Brad Dalton from Fugro to join us to share his view and vision on structured house monitoring applications for the company. And then also we have our chair of ANSHM, Professor Tommy Chen from QUT today to help us manage the logistics. Not sure whether Professor Tommy would like to speak anything. Yeah.
So thanks, Lee, for organizing that. I leave it to your capable hands. So I leave it, and also thanks Brett and John for facilitating that, and Brett for presenting in this topic. Okay, so I just be at the backstage.
Thank you, Tommy. Thank you. As well, we have John Vazzi from Analysis to help us facilitate the first web forum. So I guess, following Brett's presentation, there will be questions coming along. So I will keep an eye on the chat. And I guess in the end, John will also try to facilitate discussions and feedback. So thanks everyone again for joining us. I can see more participants gradually increasing the amount of people. So I would like to hand it over to John, or perhaps John, you can introduce Brad a little bit before the presentation. Thanks, John.
G'day. Look, thank you all for joining us. I don't really have a lot to add. Brad's coming from Fugro, who are a monster of a company with a huge background in GIS and dealing with disparate data sets. It'll be fascinating to see what he's able to present us and their vision for structural health monitoring. Go, Brad.
Okay, no problem. Thank you very much to everyone. Shishin, to the people who invited me, Tommy and Lee, thank you very much. And with that, I'll do my little best to figure out how to run this and go from there. Firstly, can everyone hear me all right?
Yes, all good, Brad.
Good. Okay, and you can see what I've got on the screen, which is the start of the Fugro Digicampus presentation.
Yes, visible as well.
Excellent. So Fugro's a very big company. We've got approximately 9,000 people that work across the world. We are the leading sort of spatial data specialists in the world. We kind of do everything from oil and gas to wind farms to structural health to just normal surveying, where we do pickups and that sort of thing, as well as aerial photography and remote sensing and so forth. So we've got a lot of different people do a lot of different things. The company is based in Holland and started in the 1960s. We've grown substantially in Australia. We've got about 200 people that do everything from be involved in launching satellites in the space program to myself that does structural health monitoring and so on. The basis of Fugro is to use what they like to refer to as our AAA approach, where we acquire geodata, we analyse it, and we give advice based on our experience and expertise. We partner with companies quite regularly. You know, John and I have spoken about partnering together, where we have a very big spatial data component, which is sometimes a bit left off with structural health monitoring because most things are relative. But there is an increasing need to figure out where things are in real world, X, Y, Z, and so on. And of course, we play across, as I said, a number of different places. Energy, infrastructure, and water on the screen is the most prominent of our places that we play. And we do a large amount with the project life cycles from, you know, start of the project and way before the start, in fact, right through to operations, maintenance, decommissioning, the whole shooting match. We're involved in every step of the process, which explains why not only do we have 9,000 people, but we're also starting to get involved in structural health monitoring in Australia, having done that in Europe for quite a long time. Today, I'm going to talk about what we call our Digicampus. Basically, Digicampus is a whole bunch of different techniques and instrumentation that we've developed over time in order to allow us to measure structures and assets using things like remote surveying, thermal imagery, and visual vibrometry, as you can see, that have, you know, aims and I suppose desires that stretch beyond the normal measurement cycle, where, you know, you go and put a whole bunch of instrumentation across a whole a bridge or a structure or an asset, whatever the case may be, with the aim of trying to get, you know, measurements on things related to how the life of that asset is going to sort of roll out. The way we look at it is that some things like that bridge that's in the background there are, you know, really hard to get to. Trying to put prisms all over that, or put extensometers, or, you know, any other sort of contact measurement devices is a very hard thing to do. So is there other ways to do it? So we started with this idea that we would measure vibration on that bridge. That bridge is in Holland. As you can see, it's a pretty major one. It takes a lot of traffic. You know, obviously can't shut things down too much. And what what we were asked to do is they had some cracking issues, and they were trying to identify where and when they occur. And so we started off by basically taking some video using a number of different techniques, but we also had some algorithms we've written that allow us to take long periods of measurement and turn it into the video that you see. We started with vibration, but we also, measured a whole bunch of other different things. So post that, we then looked at the idea of on this same bridge of measuring it instead of underneath from the side, which presented itself as a better way to measure what was going on, to figure out where the waves that are produced as traffic runs over the bridge were promulgating and concentrating. And you can see pretty clearly on that image where that was occurring. So to do that, we used a number of different techniques, but we also, in the process of this, developed some in-house algorithms to be able to analyze the data very accurately and spatially locate the things that needed to be identified, so that if there was a need to get onto the structure itself and put things in place, we knew actually where to put them rather than just trying to cover the entire structure. So from that, we then went to the idea of let's have a look at it using thermal imagery. The whole idea of the thermal imagery was to see if we could identify various different things that occur, because obviously if you've got a crack or a warp or something like that, and you've got movement going over the bridge, it creates a little bit of heat, and you can actually measure that if you have a camera with enough resolution in terms of the thermal range. So from that, we managed to come up with a graph that showed over time what was going on with the structure, how much it was heating, where things were happening. But of course, the thing, was very obvious, and you guys would know this quite well, I'm sure, is that over time, things heat up and then contract and heat up and contract, and you can be very, very confused or very uncertain as to whether the result is actually trying or showing you something that's real, simply because of the time between, one measurement and the next. The sun might come up, get to 30 degrees, go back down. At night, you're down to 9 degrees, and everything moves, and it would appear that there's movement, but in fact there's not. So one of the whole ideas of this stage of the work was to try and identify when those things occurred. Excuse me, I need to take a drink. Frog in my throat. So from that, we then went to a point where we could start to identify where cracks occur. So if we go back to this diagram, what we then did was focus a camera on where those waves are occurring most obviously, in order to see if there was a crack. For this, we used the Metrum product, and I'm just going to play a video here which shows you as traffic was passing over the top of the bridge and creating movement and vibration, you could see a crack start to appear in the analysis of the data. And you can see that very clearly as each car goes over the top of it, the crack just opens up a little bit and closes a little bit, opens up a little bit and closes a little bit. So from a spatial perspective, we were able to identify the X, Y, Z of where that was occurring. From the analysis, we were able to give them a magnitude and understanding of what was going on and when. And obviously from a remediation perspective, they were able to go and treat that and deal with it accordingly based on the data. And over time, we managed to identify, I think there was something like 50 or 60 cracks in place along the bridge that allowed that asset to extend its life by treatment. And it was just the process of those 3 sets of different readings that allowed us to narrow down very clearly on what it is that we needed to address, or what, more importantly, what the structural engineers needed to address. Having said that, we then went back to an original idea of measuring the vibration and comparing the set of movement we got out of one set of instruments to a laser device, which you're all, I'm sure, fairly familiar with, just to see whether or not the camera was giving us a similar result to what the laser would give us. Obviously, the laser is very pointed, whereas the camera is pretty broad. So we had to move things, around a little bit in order to be able to get a measurement. And so that meant that we had to, if you like, kind of align everything up time-wise or temporally together in order to get a comparison. But it showed pretty clearly in the end that, over time, we were measuring fairly accurately using the standard laser method against the vibration camera. This is what it looks like. It comes with its own box and housing. The whole idea is that you set it up, leave it in place for a period of time. It's not long. It's not one of the systems that you can set up and walk away from. Well, if you want it to still be there at the end of the day, you don't walk away and leave it. It's a little bit expensive to have put in the back of a car and driven off at speed. So the whole idea is you set this device up, and it's connected to its own box, which you see there in the middle of the screen. Has a computer attached to it, which does recording, but also has the analysis capability. That's actually a screen that's in the middle of the lid. So you can bring up the data, check it on site, make sure that it's all valid, that you've got what you needed, and then you can take it back to the office and process it. Having said that, you can actually process it on site as well. But when you combine it with some of the other instrumentation that we use and put it into our Digicampus format, you're able to get a fairly clear idea pretty quickly of what's going on with the structure without having to climb on it, touch it, or otherwise. And that's the whole point of this, I suppose, this measurement system, is to try and get away from the idea of hands-on structure or people on structure and safety issues that go with it. So following that, we were asked to go along and measure a bridge that has a train that runs over the top of it to see what's going on. I'll run this video for you. You can see on the right-hand side the various different displacements that we measured. Now, the way that this system works is that it's a relative measure. So it goes looking for things that it can identify that are not going to disappear as vibration occurs. So typically speaking, it'll latch onto all the bolts that you see in the bottom three squares, and as, whoops, pardon me, and as the train goes over the top, you can see it's going over the top. You can see all the readings that are occurring simultaneously, and it's identifying where all those points of commonality are by those little, if you can see them, I'm not sure if you can, but I can see them, the little crosses that appear on the understructure. So as the train goes over, those points will vibrate in relation to each other, and it's a relative displacement that occurs. So, to do this, to do that, and so on. But the beauty of it is that you can capture the entire bridge all at the same time, and you can get very high accuracy out of it. You don't have to measure one piece and then another and another if the structure is small enough. Now, clearly, if the bridge is 2 kilometres long, it's a different story. But if it's relatively short, like this thing, I think is about 50 or 60 metres long, we were able to sit to the side and then go over to the other side of the bridge, measure the same thing in a different direction. There's points of commonality that occur from both sides, so we can tie them together. We can get out a total station and, if necessary, shoot reflectorless onto some of the structure itself to put some X, Y, Z in real world or absolute coordinates around it, and therefore do some pretty good analysis. The data that's recorded is multifaceted. There's a whole bunch of different analysis that you can do in the back of this from the data. It stores everything that it sees. So you can set up the way that you want to analyze that data. And when we read it into our Digicampus and Vertigo software, we often are asked to go and have a look at different elements that we hadn't thought of at the start. Let's zoom in on here, or let's play with that a little bit and see how it goes. From that, we identified on the structure that there was a part that needed to be measured. So this is as the train goes over, and you can see that's having a fairly severe and obvious effect on what's going on. And you can see the relative displacement that is occurring over time as that occurs. And then, of course, as it gets to the end, it's going to settle. And so we were able to, in that same day and the following day, just focus on the various different elements that they wanted to get more precise or more high resolution information on, simply because this rail line happened to be one that's got a train going over it every 5 minutes or 10 minutes or something like that. So it wasn't hard to move it around from one location to another to see what was going on. Then following that, Fugro went down the path of trying to work out a way of doing measurements where it was cost effective to put a optical device in place that gave surveying type measurements rather than this straight displacement. And the difference there, of course, is absolute versus relative. As much as it doesn't look like it, this thing is actually a total station. It's a total station that's based on the idea of a camera. It needs, this is the one thing about this that is probably not ideal in terms of what we've just been speaking about. It needs prisms in order to measure to. But you place those after you understand what it is that you're going to do, and then you can put this thing in place permanently to monitor what's going on. The beauty of it is that it sees all of the prisms simultaneously. So as opposed to a total station, which goes measurement, 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 measurement in an array, and you have a temporal shift between measuring prism 1 and prism 15, for example, and then over the whole array, you might have 15 or 20 minutes of work. This thing can go snapshot, and it gets every prism simultaneously. And it's cost effective. In comparison to a total station, it's about 1/5 of the price. It's been developed in Holland. It came out of the oil and gas industry where we were asked to do a specific task, and we built this little thing. It's as robust as hell. You could run over it with a train and it really wouldn't do it a lot of damage. It's able to see in infrared as well as normal light. And obviously, as you can see, it's powered by solar array, but it doesn't have to be. You can run power to it quite comfortably. It works on the cloud, but it doesn't have to be. We can put a computer, edge computing device beside it. So currently, we've just, we did all the things that I've just been speaking about with the metrum and everything else to work out that this particular bridge has some issues. So they've gone and put about 7 or 8 prisms on this bridge to understand what it's doing. The question here is, does the bridge get replaced, or does it, do they elongate its life? So we put a total light in place right beside the bridge at right angles to it on that wooden pier that happened to exist at the same time. And for a little while, we ran a total station beside it just to see whether we're getting the same results, which we were. And we've been measuring that bridge for quite some time. The whole idea is that it measures from one end of the bridge to the other in one snapshot, and it does that every 1.5 to 3 minutes, depending on how often you want to set it to measure. And it does that throughout the day or night. It makes no difference. And those results are fed back to the cloud and into our Digicampus software, which the client can access. It's a bit of a game changer as far as the way that measurement systems work, like surveying type measurement systems, because generally speaking, you need to have a fairly expensive piece of equipment, being a total station that's got horizontal, vertical circle, laser involved, computer on board, etc., etc. This device is just pure optics. It's just looking at the prisms and it's working out where they are. And an example of that is, sorry, I've got them in the wrong order, but this is an example of that in action. Each of those red dots represents a prism that is actually on that bridge. As you can see, the bridge in the background is blurred. We don't need real world imagery to make it work. The way that it operates is that it sends out a flash of light and it's looking for a return off the prisms. So the flash of light that's coming back off the prisms is sufficient for the computer algorithm to narrow down on the individual prisms and then measure them all simultaneously. So if you wanted to know what your relative displacement was between 4, 7 and 4 and 6 and 4 and 3, it will tell you that at the same time, and you'll be able to see what's going on in terms of movement. The system is controlled through a gateway. You can set multiple up at the same time. The prisms are relatively lightweight, pretty easy to install. They can be magnetized. You can connect this through the gateway back to the cloud, or you can put an edge computing device beside it. It's pretty hard to knock off. As I say, it's robust. We have mechanisms in place in it to identify when things are obscured. There's a whole bunch of checking goes in the background to see whether or not, you know, a bird's sort of decided to have breakfast right beside it, or if it's got some spider webs on it and that sort of stuff. We can identify that reasonably quickly and easily. And as you can see, you can connect it via Wi-Fi or 4G, the Ethernet, NB-IoT, and so on. It's pretty straightforward. The battery is relatively low power and doesn't require a huge amounts of power to make it work. So in comparison to the other systems, it's just more an augmentation to them rather than being a standout, but there's no reason why you can't use it on its own as a normal monitoring device, just like you would a total station. The applications for what we see the Digicampus product being is everything from you know, construction through to waterways and railway and mines and so forth. As you can see on the screen, we've got a lot of different applications for the things that we do. It's not just total light there. It's, you know, it's a whole bunch of measurement devices. After all, we are spatial scientists. So and obviously we've got offices all over the world, so we get to play in a lot of different spaces that in Australia, you know, you wouldn't find easily. And then obviously the last thing is, you know, what do we learn out of this? And you know, the things on the screen obviously explain in detail what we found and where we've decided to focus our efforts and try to improve on our systems and the way that we look at things. Some of the issues that we've faced along the way, you know, things like coding and shadow is a pretty big one. It happens in lots of different places. And obviously, you know, the ability to measure high fidelity, low frequency, as well as really high frequency, you know, things that dependent on the situation. So with that, I'm pretty much done. And I'm happy to take questions. Thank you for having a listen.
Thank you very much, Brad. That's it's really interesting. I'm going to hog the stage now, John. One of the things we've found very difficult with optical base systems is the referencing. The poles get hot and cold, the sun goes up on one side and down on the other, and all of our imagery is constantly sort of moving relative to. How do you reference your image systems, and how do you get around that problem?
So as far as referencing is concerned, we put we would usually go out with a total station and measure to a number of points over periods of the day and try to develop a model around temperature variance and how much things can expand and contract. You can use a total station with a reflectorless on it, or you can use a prism or stick-ons, little square stick-ons. I'm sure you're aware of them. But with those, we're able to measure to things that are off structure, that are nearby, that in field of view, and that gives us the ability to kind of, in a way, resect everything else, because you've got these fixed things that are on the outside, as well as the moving things in the middle. And that becomes really relevant from a spatial perspective if you want to get absolute to relative, or relative to absolute. Those things are really important in terms of planning.
Yeah, cool. And so in the way that you've set them up, the images you showed, most of the prisms were actually on the structure, but you do have a couple of references within that on things that you're not expecting them. Yeah.
Yeah. sorry, I was just going to say the structure with the bridge with the total light off it. There's a couple of prisms which are in the embankment to the side, which you can't see, but they're there.
Yeah, cool. The other thing we've had real trouble with is the scaling on these digital systems. You've got the variations in parallax and depth of field, where pixel means a different thing depending on where it is in the image and where it is within the lens set and where it is on the structure and its proximity to you. How do you get around that problem, and how do you scale?
Well, one of the things you have to do with the lenses that we use is have a calibration done. Radial distortion is a problem, but it's a relatively well-known one if you've got a very well-manufactured lens. They cost a bomb. You don't go and buy them at Bunnings, for example. But you can put the lens into a calibration device, and essentially what it will do is move around the lens and shoot light through it, and that will allow you to work out what radial distortion you've got. So that's a reasonably common thing to do with camera systems, particularly large cameras that have got big lenses on them that you use for aerial photography. They've been doing that since the 1960s. It just means that you need to have the resources to be able to do it, because it's not an easy and quick thing to do.
Yeah, right. So you don't scale off the image itself. You calibrate the lenses, and you walk into field with calibrations. That way you can walk up to a bridge and you know that you've got 2.6 millimeters of vertical displacement given your proximity to the bridge. Yeah, and I guess you'd have to give it range. Is that how you do range?
You have to take a shot with a handheld laser to the center and to the edges of the image in order to get enter that into the algorithm to work out, allow it to work out what it's doing. But pixel resolution is not about absolute measurement for the most part. It's about relative displacement. So as long as the two things you're trying to measure are not miles apart, relatively close, the radial distortion you're going to get is relatively the same. And I noticed we had a question about what sort of camera we use. A very expensive one, as it turns out. The cameras that you need to use for it are not a Canon that you might go and buy at your average camera shop. They're the cameras that you have to go and get specifically for task. Having said that, they're not $100,000 cameras. They're in the tens of thousands, I suppose. But you use them for a very long period of time. So it's not a case of you need to go and buy a camera and then 3 months later go and buy another one.
That's fun. For the presentation, sort of question. Because we talking about the 4 meter length and the accuracy almost about 0.1 millimeter, 0.1 meter. So is that possible to have a look at the much lower measurement, getting close to some probably less than a millimeter to determine the displacements? That's one question. The second question is, how do you clarify the results? Because since this is a wave-based transmitting the data from the lenses to the camera, how do you minimize the noise ratio? Because that could have a lot of effect on the traveling wave.
Yeah. So with the camera systems, the algorithms have been built since the 1980s, I believe, and they've done a lot of work on that in the background. So my understanding is that it's all built in the back end to deal with exactly those sort of issues. And your first question of can you get better than 0.1 or a millimeter? Yes, you can. It becomes a matter of a controlled environment. In other words, you got to do things like get close, take temperature readings, pressure readings, and so on, so that you're getting an understanding of the atmosphere that you're playing with, and you enter that into the software in order to tell it right now what it is. Plus, it's got inbuilt pressure and temperature gauge within that box that I showed you. But you want to verify one against the other and make sure that you're not getting a bodgy reading. but the real answer to it is get close. You know, if you want the total light or the Imagery system to work well, you want to get relatively close to the subject, and by that I mean within 50 meters, right? You can run it from 250 meters away, but you're just not going to get a millimeter accuracy. You're going to get more like a you know, 3 or 4 millimeter accuracy because you're just so much further away. But it's horses for courses, you know, because the fact is that in every case you're trying to solve a problem, and you got to be careful what problem you ask. But you know, you'd be well aware of that. That's the standard thing that you guys would be teaching your students every day of the week. So be careful of the question you ask, that you don't get the wrong answer back and think that you're getting the right one, right? So a lot of this sort of stuff comes down more to planning than actually measuring. You know, we would spend 4 days planning for, you know, a half-day capture as a minimum, so that we understood what the question was before we got out there. A bit like, you know, the old tale, if you're a lawyer, you don't ever sit in a courtroom and ask a question you don't know the answer of already. Well, in many ways, that was part of the exercise right from the get-go of this presentation, is to go out and quantify what the question was going to be that we had to ask before we actually got to the point where we started asking the question. If that makes sense.
Yep.
Thank you very much, Brad, for answering all the questions. Just repeat Tommy's message in the chat. So anyone, if you ask questions, please identify yourself with your names and affiliations so that I can better collect these profile. Thank you very much. Yeah.
And answer to Andy's question, so you show applications with steel girders where you have good spots like bolt stitches, target points. Have you dealt with concrete structures? Yes. Do you use speckles? If you get really close, bit like the speckles on my forehead, right? You know, you're getting pretty close to see them. Now I'll show you what I mean. But you know, if you're not relatively close, then you need to have something that stands out. Now, if you need to do that with concrete structures, it may be that the thing that you go looking for is a target that you put in place, which is not ideal. But generally speaking, concrete structures have, you know, expansion joints of some description. I mean, you know, if it's a bridge, you got T-beams coming together. The software will identify that the corner of where those bits of concrete come together. So as long as you've got something that it can go, okay, that's what I'm referencing, and that's the thing I'm moving, that's moving, that's what I'm measuring against, then you have a way of dealing with that. So next one, how does the Imagery perform when we measure displacements for a long period of time, half day with changing light conditions? It doesn't really care that much. Obviously, light conditions where you have the sun going down and the sun coming up and it's directly behind the lens, that's not ideal. But then again, going back to the planning thing, you don't do that. Shadowing doesn't appear to affect it much. You can have shadows occurring as the day progresses, and because it's kind of what it does is it kind of opens the aperture and just keeps measuring. So as the shadows move, it's only using kind of 1 or 2 things, or maybe half a dozen things to reference. So if they go in shadow, it still sees them, even though it might be black now and it might have been a little bit wider half an hour ago. That doesn't appear to affect it. Again, in the back end of the algorithm, it's been kind of addressed. Is the best way to describe it.
Thanks, Brad. I also pick up a question from the chat history by Vahid. So not sure whether you answered this question. Can you please explain what kind of cameras did you use for image-based measurement? Yeah.
So the camera we use is not an off-the-shelf camera. You can use off-the-shelf cameras. You just won't get the high degree of accuracy that you might be after. But generally speaking, the lenses that you use are supplied by Imagery, and they are pretty, what would you call it, very well manufactured lenses that don't have a lot of radial distortion issues. In other words, the lens is uniform, and you have to have a very controlled environment to build a lens like that. And so as a result, the camera systems that we use are tailor-made specific for the situation. If I may, I'll just quickly go back to the picture at the start, which shows the camera that was used. Let me just go and find it before I bring it up. There it is. And I'll go here. Oops. Sorry, bear with me. Right there. Right, so you can see that the camera that's used in that image is a relatively robust camera lens. It is connected to the Measument system. So that box that's sitting in the back, that's actually the array itself. That's the actual camera. The lens in front of it is a zoom lens in this case. There's a number of different zoom lenses you can get for different lengths and distances that you want to go to, different fields of view, and so on. There's quite a selection, if you like, and it's got to do with, you know, horses for courses. What are you actually trying to measure? Okay, next question. The measurement of the displacement is more sensitive determination of the existing pre-stress force. Any environmental effects to be considered? Yeah, plenty. Again, you want to plan it so that you don't necessarily want to do it on a rainy day or a cyclone's blowing through or anything like that, or it's 47 degrees and in the shade with 700% humidity. Our general suggestion is don't do that. Try and take it at a time where you're dealing with standard temperatures and pressures. Anything from say 15 degrees through to about 30 is just fine. Obviously, if it's a really hot day, you want to have the camera lens under a umbrella to try and deal with that. Not because you don't want it to get wet. They're robust and waterproof, but you don't want it to get hot. Hot will cause the metal to move, not the glass. Now next question I've got is measuring squared on from side is best position. Have you verified when you position the camera is not square on? Yes. We've taken quite a bit of imagery where the camera hasn't been pointed directly at the target. It really doesn't care. If it's looking at the house behind me over in that corner over there, it's looking at that part of the door, and it uses that as a reference. As far as it's concerned, it's looking straight at it. It just happens to be looking at it from your perspective from the side. What if the total light gets hit or impacted for whatever reason, unintended monitoring? Does that affect the high quality of the system? Does it recalibrate itself or need a manual reset? If it copped a big enough bang, the system would actually send me a message saying, I've just been run into by some idiot with a train. Come and help. But if it copped a bang like a bird landing on it, because you put it on a pole, it's pretty robust. It's unlikely to do it to reset it. And bearing in mind that the thing measures from, it's a relative measurement. So what was it a minute ago? What is it now? What was it, an hour ago? What was it a day ago? So if you have a slight bit of movement, or even a bit of movement that's not insubstantial, say, 50 mil or something like that, it's still looking at the same things. So it's able to go, all right, well, a little while ago I was looking at it from this angle and the measurements were all this, and now I'm over here and the measurements have changed slightly, but have the relative measurements between each series, have they changed? And the likelihood is that that's not, that they haven't. So from that, you would know that you've got potentially something you need to look at post-analysis, or you just simply go, okay, well, it doesn't appear to have made any difference. All of those things would come up in the software and let you know that there's an issue. Mary's asked, is there a published data validation approach for both the metrium and total light for our reference? For total light, we've got them internally, obviously. We've been measuring in a number of situations with a total station and the total light running side by side. And that has been going on for some time. It's probably a good year now, as we've refined our approach and the way that it works. And Metrium have got stacks of data. Are you able to access the total light information? Not for a little while yet because we've got a patent pending, but there will come a time where we'll be able to publish that. For the metrum, I would imagine if you asked me to ask them, I could probably find the answer to that out without too much trouble. The next question is the vibration introduced by an earthquake or ground motion? The camera is vibrating as well. Can it still measure accurately? Well, probably. The trouble, of course, is that everything's moving at the same time. You're going to have a pretty good algorithm to try and work out what's going on. Going back to John's question, if you're measuring to fixed prisms or fixed targets, fixed bolts, whatever, overhead gantry that's not going to move, and you're trying to measure the difference between that and something it is, but it's moving as well, then that becomes a little bit of an issue. But then in response to that, I'd say, as people, we're moving through space at a fairly, fast clip. We're all moving at the same time. And, when the wind is blowing, it's moving slightly faster than the Earth is. So we still manage to measure with those sort of things in place. So I can imagine it would be an issue, but not a huge one. But then, of course, it depends on how much it's vibrating, right? If it's a big enough earthquake, I'm not sure that anything's going to be able to handle that. Frank, you're welcome. Can one camera focus on many points? Yes, absolutely. The whole idea of both these systems is that you can measure all things simultaneously at the same time. That's the real point of this. As opposed to going out with a total station and measuring through an array over a period of time. The camera and the total light are set up to measure simultaneously to loads of different things at the same time. And I'd have to say with the metrum gear, if you decide later on that you want to change your reference point and measure to something else, because you've got the data recorded, it's been continuously recording the whole time it's been going, you're able to go, oh, well, now I want to reference everything off that rather than this. That's pretty easy. Leah, thank you very much. No problem. Lawrence, any need for a reflector at a target point? Can you explain that a bit more, please? I'm not sure what you mean.
Hello, Brad.
Hi.
Yeah, what I mean is that your camera just only focus on one point and directly collecting signals. Is that as simple as that?
No, it's everything within the array is considered to be a target for the metrum system. Everything, because it pixelates everything, and they're pretty small pixels, right? So it's essentially measuring pixel to pixel, but it's a little bit more complicated than that. That says it very simply. But the reality is, everything in field of view is relatively within the frame of the calculations that will occur. Having said that, if you measured to the white wall behind me, it would just see a white wall. It would see the lines between the planks as an individual object, but the white wall would just be a white wall.
You just make your own reference to any point. Okay.
Yep. You get the mouse and you go, I want to use that as a reference, and then you go and use that as a reference, and away it goes.
Oh, okay. So
but you can rerun it, right? So if you've the point is that if you don't, later on you go, they weren't really the best things to use. Let's try it with something else. You can rerun the simulation and rerun the analysis and go, I'm going to use this one and this one now, or this, and this. Drop them in and out.
So this is simply an optical camera.
Yep.
Okay. Wonderful.
Yeah, a little bit more sophisticated than that, but you got the idea.
Yeah. Okay.
Thank you. Next question. No problem. Vade, can you introduce references for the method that a metrum uses for measuring the vibrations? Yeah, you can. You could put a target up in place and say I want to use that, but you don't need to because it does it itself. But if you wanted to be climbing on the structure, which is generally speaking you don't, but if you did, you could put a tape measure up there or a ruler and stick it to the structure, even one that had small graduations on it, and it would be able to see that. And then you'd get some idea of what's going on. that's possible. You don't have to use a ruler, of course. You can just use a sticky piece of paper that's got the graduations on it, or a barcode or a QR code, something like that. All those things are possible. I mean, as the images are continuously obtained, this will require huge data storage. Not really, not in today's time and frame. With terabyte coming in a box this big, my phone could do most of what's needed here and store it, so that's not a big deal. The only drama is when you want to take that data and throw it across the cloud. Terabytes, are slow to upload, particularly if you've got bad connections. But with the Imagery, it stores it on inside the box. With the total light, it stores it and then sends some of it out. There's some stuff that goes on in the background that I can't really talk about too much, but the idea is not to send great loads of data out at any given point in time. On that, I'm old enough that I used one of the first total stations in Australia, and we had 16 kilobytes of memory to play with in those days. So it makes a terabyte fairly amusing in a way. Okay. I'm at the bottom of the list. And no problem, man. Happy to answer that.
I can see that there are more questions coming up. So,
Mary, yep.
Yeah,
it was slow loading. What frequencies can the system cover? Pretty high frequencies to pretty low frequency. You can go at 2 hertz, and I believe you can crank it up quite a lot beyond that. The question is not quite so much what frequency you want, but what you're actually trying to get out of that. But I believe it's in the hundreds quite easily. But again, that depends on how close and what you use as reference targets and what you're trying to measure, right? So horses for courses. A bridge is very different from a lab with a small piece of metal, right? Vahid, is there any sample data available for the Imagery? Yep, plenty. You just have to ask Lee or Tommy, and they'll ask me, and I'll be able to supply you with some of that. Generally speaking, what I'd say about the system is we rent it out to the people that need it, and we obviously have a trained person like myself that comes along and uses it. For the most part, we don't sell it. We just provide the service. And if anybody's got any projects that they think it can be used on, more than happy to have a chat. No problem, Mary.
Can I ask one more question? I'm asking so many questions.
Yeah, that's all right. Asking for a friend.
So it's good. It's pretty good. The work. I really appreciate that. Just a question in regard to the interfere that can happen between the Imagery and the actual lens. So I don't know, such as because it's based on the wavelength and the lighting.
Yeah.
So did you ever experience like any interference? I don't know, some kind of huge.
Yeah, you do. Birds fly across the thing. On occasion. Adventurous birds don't kind of listen to surveyors and go, get out of the way. But it really doesn't matter if that happens, because it's a continuous feed, right? So providing you don't have a truck that comes and parks itself in front of you, or a boat or a train or something like that, it stays there for the whole length of time you're measuring. Generally speaking, you can just edit that bit out and go, listen, from here to here, I don't want to do analysis, right? The software is smart enough to deal with people who are not smart. No problem, John.
Do we have any other questions? Okay, so thanks very much again, Brad, for the wonderful presentation. Interesting, and I can see that we are very responsive to your questions, so that makes you keep talking to us and without drinking water later on. So I guess it's a very good practice that we start to run this kind of web forum, our web forums on a regular basis down the track. And today obviously is our first one, and we have 28 participants, which is an evidence that this kind of discussion is meaningful and beneficial to both industry and academia. I can see Tommy is on his camera, so yeah, I would like to pass it over to Tommy.
No, I just would like to say thank you for Brett and John and yourself. So we will keep organizing this kind of webinar. It seems that quite a lot of people are interested in those topics. So thanks for attendance, and thanks Brett, thanks John.
And the last thing I want to say, if I may, is that Fugro later in the year will be looking for anybody who would like to participate in trials of the total white in Australia if they've got some project that they think might be relevant for. We're very keen to find participants to partner with us to do that.
Yes, and just one last advertisement is about the ANSHM 15 workshop. So please, that will be in November from 24th to 25th. So for those who are interested as a camp, you are welcome to attend. Maybe I showed the flyer. Yes, so this is the. So I just share the screen, and so this is the information about these workshops. So for those who are interested, please mark that down on your calendar, and I will keep updating the information about that 15 ANSHM workshop in my monthly update. Okay, so Lei, I just leave it to you to conclude this webinar.
Okay, thank you, Tommy. And once again, thanks for the presenter Brad from Fugro, John to facilitate, as well as our audience. So after this presentation, if Brad, you don't mind, we will publicize to our ANSHM YouTube channel, so everyone can watch your recordings later. So thank you. Yeah, and once again, thanks for everyone for joining us today. It's a wonderful discussion. So once we have a plan for our next, web forums, we will distribute information, and we invite more participants and presenters to coming up to present your structural house monitoring applications. So thanks everyone again, and wish you a good day. All the best, and see you next time.
Bye-bye. Thank you.
Bye.
Thank you. Perfect. Thank you very much.